Hey Level 3s, this is your first tutorial session for the further assessment opportunity on redox. So I'm going to do 3 videos. The first is going to be on electrolytic cells, the second will be your galvanic cells, and the third will be talking about specifically how we can compare and contrast these. So first of all, electrolytic cells are the non-spontaneous cells. So this means that they need a power supply, and the reason why they need that power supply is to push the electrons in the opposite direction that they would naturally want to go. For this type of cell, there are 2 types of electrolyte. Electrolyte is what the electrodes are placed in, and they can either be molten or aqueous. So let's run through an example. It's easiest to teach this all through examples. We're going to do a molten one. Molten are by far your easiest type of electrolytic cell because exactly what you expect to happen happens. So the rule is C to C and A to A, which means cations to cathode and anions to anode. So we can draw a template cell, and you're all really good at this. So we do a power supply at the top. We do electrodes coming off that, and they're in one beaker or one cell. Okay, so let's just fill in our template and then we'll fill in the detail of this cell. So electrons will always flow from the anode to the cathode. That's same for both electrolytic and galvanic cells. This is the cathode on the right. Conventionally, we do the cathode on the right. I always get my students to put cathode and then reduction because that's always something that stays the same. Reduction always happens at the cathode and oxidation always happens at the anode. So this is kind of your template so far that you can always do. Now, if anions are going towards the anode, and anions are negative ions, okay, that must mean that the anode must be positive because opposites attract. So your anode is positive and your cathode is negative. I'm just going to state here, but I will restate this later on, those charges flip when we turn into a galvanic cell. So down here, I'm going to write what my electrolyte is. Today it is lithium chloride liquid. The liquid means molten. That's simply an ionic compound that's been heated up and it's in its liquid state. So the ionic lattice has been broken down and the ions can move. That's the principle by which this allows to happen. Cool, so we've got our cell, and so now we can actually add some details. So it's exactly what we want to happen happens. So our oxidation equation is going to be anions to anode. So what are our anions? They are the chloride ions, and they're going to go to the anode. So we've got chloride ions, they're liquid state. You must have states at level 3. Okay, they're liquid because we're dealing with a molten electrolyte. And so chloride ions are going to form chlorine gas. The hard part about this topic is you do actually need to know what species form. However, you do get a bit of a helping hand with your reduction potentials. Apology, that should be up there. Okay, so we need to balance this out first of all. So we're going to do our half equation. You've got 2 chlorines here, 1 chloride, so we need to put a 2. And then we don't have any oxygens or hydrogens, so we're just going to balance the charge. 2 negatives on the left, which means 2 electrons on the right. So this is also confirming for us that this is oxidation because we have got a loss of electrons. And you need to specifically say that in your internal assessment, that loss of electrons is oxidation. I would prefer you to state the number. So loss of 2 electrons is oxidation in this case. We're going to quickly do oxidation numbers while we're here. You forget the 2 in front when you're doing oxidation numbers. Chloride is a monatomic ion, which the rule for that for an oxidation number is it's the same. So therefore, the oxidation number of chloride is -1. We put the charge before the number. The oxidation number of an element, of which chlorine is 0. So what we can see here, team, is that this is an increase in oxidation number, and an increase in oxidation number equals oxidation. So you have to specifically state that in your internal, that loss of electrons is oxidation and increase in oxidation number is oxidation. Cool. Let's now do reduction. Okay, so cations go towards the cathode. So Li plus, you always start with what you've got in your electrolyte. So we start with chloride and lithium ions because that's what we've got here. Gaining electron to form Li. And the metal will still be in the liquid state. So it will go onto the electrode, but due to gravity, it'll flop to the ground. So it'll form a pool here and they siphon that out the end. So it'll be liquid state too. Okay, so the oxidation number, monatomic, so it's +1 and it goes to 0. So this time it's a decrease in ON, which confirms reduction. So now we need to do a full equation. Okay, so to do a full equation, we make sure the number of electrons are the same. So we have to times this equation by 2. So it's going to be 2Li plus liquid plus 2Cl minus liquid goes to Cl2 gas plus 2Li liquid. Okay. The next thing that we're going to talk about now are observations. Now, you should write it in a sentence in your internal, but it's totally fine to actually write it underneath the species because that will actually signify to me that you're linking it to a species. So if we've got Li plus is going to be colourless. Okay, Cl minus, colourless. Cl2 is a pale green gas, and you do have to learn these colours. There's actually no easy way around it. I'll give you some hints at the end. And Li is a grey metal. So some hints with metal colours, they're probably the easiest. All metals are grey, except for gold, which we say is yellow, and copper, which we say is pink. You can't describe silver as silver because that's actually its elemental name, so it can't also be a colour, it's its elemental name. I know we commonly describe things as silver, but you can't do that here. So now we've done colours, we've talked about a gain of electrons equals reduction, and a decrease in oxidation number equals reduction, a loss of electrons is oxidation, and an increase in oxidation number is oxidation. So far, this aspect here on the left hand side of the screen is actually all level 2. That's all level 2, and this part here is your level 3. Okay, so we've actually done your first type of cell. The only final thing that we can do is we can prove that this reaction is non-spontaneous by working out a cell potential where we use reduction minus oxidation. So what's getting reduced here today is the lithium. Okay, so that's going to be -3 minus 1.36, and that'll give you a negative number of, because a minus and a minus, they actually add together, so it's going to be negative 4.36 volts. So that's going to be negative. Okay, so therefore, because that's negative, it is non-spontaneous. And we'll talk in detail in the compare and contrast about that. So well done there. That's the first example. Okay, so we're going to move on then. Example 2 is the second type of electrolyte, which is an aqueous electrolyte. So there are a couple of points we need to make, some general statements here. The first is that the rules are your anions always go to the anode. There are 2 exceptions, which you do need to remember, and that's nitrate and sulfate. So if you have these anions, they actually can't get oxidized further. And if that's the case, water ends up getting split and it forms oxygen. So you do need to remember that. All other cases, the anions will go to the anode. The hard part here is, will cations go to the cathode, or will water get reduced? So to do this, we have to use reduction potentials, and we'll run through some examples soon. Just a quick note about water. So water can actually be split with a power supply, which means that it can actually undergo oxidation and reduction. So the water can be oxidized to oxygen. Okay, so if we balance this equation out, if water forms oxygen, you need to have 2 waters to balance the 2 oxygens. We then need to add 4H plus, and then to balance the charge we need 4 electrons. Electrons are being lost, so it's an oxidation reaction. Now, because we know water is neutral, if this reaction's acidic, then the water getting reduced to H2 must be basic, and I'm going to run through now how we come up with this basic equation. It's the only basic equation you need to know how to do unless you're doing scholarship. So how to balance in basic conditions, I'm going to run through the example here. Step 1, you balance it as per normal in acidic conditions. So this is water to H2. To balance out the fact that you've got 1 oxygen here and none here, we add a water. Okay, now we need to balance the fact you've got 2 hydrogens, and 2 hydrogens makes 4 hydrogens, but you've only got 2 here, so we add 2H plus, and we balance the charge by adding 2 electrons. Hopefully we're all good with that by now. So the next step is you add the same number of hydroxide ions as there are H plus ions to each side. So we've got 2 H plus ions here, so we add 2 OH minus ions here and 2 OH minus ions here. The next step is that we cancel out our H plus and OH minus, so these 2 together make 2 waters, and so I've done that here. So I've got 2 waters here. Okay, the final step is just to cancel out if you've got extra waters on each side. So what you'll see here is you've got 1 water here and 3 waters on the left hand side. So we're just going to knock this one off and then change this to being 2. Okay, and therefore you have your water forming H2 in basic conditions. Okay, chuck on any questions on Teams if that hasn't made sense. So let's go through an example of aqueous electrolyte. We're going to run through 2 examples of these. I'll probably have to start a second video, and that's totally fine for the second one. So again, we can use our normal template. So we've got our power supply and our electrodes. Now, I forgot to say in the last one actually, which is a bit remiss of me, is what these electrodes are made out of. So we've got a cathode here, and remember, reduction always happens at the cathode, and we've got our anode here, and oxidation happens at the anode, and we've got electrons that flow from the anode to the cathode. Anions are attracted to your anode, so that means anions are negative, so the anode must be positive, and this must be negative. In electrolytic cells, the electrodes are always inert, which means they're going to be made out of platinum or graphite, which is carbon. So platinum or graphite. And I should have done that in the last one. Sorry about that. So now we're going to put in our electrolyte, magnesium bromide, aqueous. So this cell is harder. And why is it harder? Because you actually have to take into consideration this here. Cations to cathode or water getting reduced to H2. Now, the first thing I always tell my kids to do is start with the anions because it's the easiest. So anions to anode except for nitrate or sulfate. Do we have nitrate or sulfate? And the answer is no. So anions are going to go to the anode. So I'm going to do my oxidation equation here. My anions are bromide ions and they're going to go to here. So bromide ions aqueous, there's going to be 2 of them, forming Br2 gas plus 2 electrons. Okay. Bromide ions are colourless and Br2 is an orange/brown gas. Okay, the oxidation number of bromide, we forget the 2, it's -1, and that's weird that it's done that, and it's gone to 0, so this is an increase in ON, which equals oxidation. We can also see that 2 electrons are being lost, and so that's actually 1 electron being lost per bromide ion. Okay, a loss of electrons equals oxidation. You'll see my full write-up of these when we do some example practice after the video tutorials. So the next step is, okay, so we've got, because this is aqueous, we know that in here is actually water as well. So is water going to get reduced or is magnesium going to be reduced? And the only way we know this is by looking at the reduction potentials. So we need to work out, will magnesium ions or will water, because these are the 2 species we've got, get reduced? And the answer is the species with the highest reduction potential always gets reduced, and in this case it's water. So therefore water is going to get reduced in this example. So we're going to see bubbles of bromine here, bubbles of H2 here. Okay, so H2 Br2. So let's go through the equation. So it's going to be, so our reduction equation is going to be H2O liquid going to H2 gas. Okay, we need to add a water because to balance the oxygens. Okay, from there we then need to add 2H plus and 2 electrons. We then add 2OH minus to balance, plus 2OH minus, then we cancel out that and those, and it becomes 2H2O liquid going to H2 gas plus 2OH minus aqueous, and that's your half equation. Okay, very quickly we'll do the oxidation numbers. The oxidation number of H2 in here, so -2, this is a neutral compound, it equals 0, plus 1 times 2, so each hydrogen is plus 1. Oops, that should be plus 1. H2 here is 0. That's a decrease in ON, which equals reduction. Colours, H2O is colourless, and H2 gas is colourless, as you know. Okay, so therefore that's how we do an aqueous electrolyte. Now we can very quickly do a reduction potential. So E naught cell is reduction minus oxidation. So we've got reduction, which is negative 0.83, minus oxidation, which is negative 2.37, and we end up with a, is that right? Oh, sorry, I've put the wrong value in here. Positive 1.0.